So factoring and completing the square aren't the only ways to rewrite equations for integrals. So rewriting equations so we can integrate them is a super common theme with all of the different types of integration techniques. So a lot of times it looks like factoring. So you might just like straight up be able to factor. You might be using something like partial fractions, so you don't have to worry about it being a perfect square, or you might need it to be a perfect square, so you might use completing the square. But sometimes you can't factor, and sometimes it's a little bit more straightforward than that, right? So if we're looking at something like this, the integral of x squared plus x plus 1 all over x squared plus 1 dx, right? We have this issue of the fact that they have the same power in the numerator and the denominator. So the way it is right now, there is no easy u substitution because, right, we got extra stuff. So what we could do is maybe try and manipulate like with a bunch of different u subs, or we can remember what a fraction means. It means to divide. So what if we tried actually dividing these things and simplifying it that way? So because we're dividing by x squared plus 1, I can't use synthetic division, so you actually do have to like reach back in your brain and use long division. Right, so I'm going to put x squared plus 1 as my divisor on the outside and x squared plus x plus 1 as my dividend inside. So to get x squared to equal x squared, I would need to multiply my equation by 1. So I'm going to distribute that through, get x squared plus 1. And then I'm going to subtract that whole quantity. So x squared minus x squared, that cancels out. And then 1 minus 1 also cancels out. So the only thing that's left is x. Right? And I can't make x squared into an x. So x is actually the remainder here. Right? So maybe we remember this from Algebra 2. Right? So to write our answer, we get our answer is 1 plus the remainder of x over x squared plus 1. So that means that this integral actually equals the integral of 1 plus x over x squared plus 1 dx. And then we can use our integral properties to split that up. So we got 1 dx plus another integral of x squared plus 1 dx. So the integral of 1 is super easy, right? That's just an x. And then now this second integral becomes a little easier because we can do a u substitution. So if we do a u with the denominator, right, our du then becomes 2x dx. And if I multiply that by a half, right, I just get the x dx that's left in my numerator. So this becomes 1/2 the integral of, right, my u goes in the denominator and x dx gets replaced with du. Okay, so du over u, that's going to become 1/2. I'm still going to bring down my x plus here, right? And that's going to be the natural log of the absolute value of u plus the constant of integration. And then if I substitute back in, I'm going to get the natural log of the absolute value of x squared plus 1, all plus c. Right, so little basic long division, and all of a sudden that became pretty easy split up, right? And then just do a little bit of u sub on one of them. So let's try one more of those just to kind of see how that works. Right, so it's not always that you have equal powers in the numerator and denominator. So if you have an equal power in the numerator and denominator, or if you have a higher power in the numerator, that kind of signifies to you that you want to do division. So here we want to integrate 2x cubed plus 5x squared minus 3x plus 4 all over x plus 4. So this one's really nice because you're dividing by a linear binomial and the coefficient of x is 1. So you can actually use synthetic division here. So if I do some synthetic division, I would put -4 in the box, and I like to label my columns so I remember what they stand for. Right, so putting my coefficients of my numerator across the top of my synthetic division chart, right, drop my first coefficient down, right, if I multiply, I get -8, it's going to give me -3, that's going to give me +12, if I add that I get 9, and then -36, so I'm going to get a remainder of -32. So my synthetic division tells me that this is all equal to 2x squared minus 3x plus 9 minus 32 over x plus 4. So I can rewrite this integral using the quotient. Right, so those are equivalent statements. And then the first three terms are a nice easy polynomial, so I'm going to break that off into its own little integral, and then I'm going to pull the constant negative 32 out. That's just kind of my inclination. So now I can really easily integrate the first one, right? So I'm using my power rule, so I would get 2 times x cubed over 3 minus 3 times x squared over 2 plus 9x, right? Technically plus c, but you only need one constant integration, so I'm not going to put that on yet since I still have to integrate the other one. And then in this other integral, right, because I have a linear and apparently a typo, let's try that again, right? That should have been an x plus 4. Because I have a linear term in my denominator, it's a really easy u substitution, right? Because if I do that, then my du is going to equal just dx. So this is going to become du over u, right? And that's that very easy to integrate natural log. So we get minus 32 natural log absolute value of u plus c. If I simplify this polynomial, I get 2/3 x cubed minus 3/2 x squared plus 9x. And then if I substitute back in for my u, right, because I want my whole equation to be in terms of x, not just the first part, right, I get 2/3 x cubed minus 3/2 x squared plus 9x minus 32 natural log the absolute value of x plus 4, all plus our constant integration.